So we've talked about the heat of fusion and vaporization before, but now we're going to actually use those things in a calculation. So remember, this was the delta H of fusion, the delta H of vaporization on our heating curves, and it's the amount of heat that's needed to change phase from, solid to liquid, liquid to solid, liquid to gas, gas to liquid. So again, it's a measure of heat. So heat of fusion and vaporization. Now, we've been talking about this equation Q equals mc delta T, but it doesn't work for the plateau of a heating or a cooling curve. Now, why not? Well, there's no change in temperature. Remember, our change of state or change of phase, so solid to liquid, liquid to gas, or vice versa, it doesn't have a change in temperature when that material actually is changing phase. So because of that, mc delta T, that would just be zero. And therefore the heat added or the heat taken away would just be zero. But we know that we are adding heat. They need energy, right? These substances need energy in order to change phase. They need heat to change phase, but we have no change in temperature. So we can't use this equation. We have to use a different equation for phase changes. So this is the equation that we use for phase changes. Q is equal to m delta H, where delta H is our enthalpy term. Remember, that's the heat of fusion or the heat of vaporization. So it depends on which phase change they're going through. And it also depends on what direction we're going. If we're going from ice to liquid, remember we're adding heat. If we're going from liquid to gas, we're adding heat. So that delta H will be positive. If we're going from gas to liquid, we're taking away heat. If we're going from liquid to solid, we're taking away heat. So the delta H will be negative. So it really depends on which way we're going on this heating curve, which actual phase change we're going through, and what substance this is. So there are a bunch of different delta H's for a bunch of different substances, and that is a constant for that substance. So you can actually look these things up online. You can look up the heat of fusion for water, or you can look up the heat of vaporization for, liquid water to steam, and it will be a specific number for that substance. So heat of fusion, or delta H fusion, is the energy needed to melt or freeze 1 gram of a substance. And remember, this is the bottom plateau. So we're going from solid to liquid or liquid to solid. And then the heat of vaporization, or delta H of vaporization, is the energy needed to vaporize or condense 1 gram of a substance. This is the top plateau. So this is going from liquid to gas or gas to liquid. So this is all a lot. It'll make more sense when I actually do an example. So here is our example. We have how much heat is needed to heat 30 grams of ice at negative 12 degrees Celsius to steam at 126 degrees Celsius. Now we have a lot of givens here. Number one, we have a mass. So the mass of ice is that, 30 grams. All right, and then our initial temperature is ice. So we have ice at negative 12 degrees Celsius, and then our final temperature will be steam at 126 degrees Celsius. Now, there is actually a lot more information that we're not specifically given, but we need to look up. So those things are, number one, our specific heat of ice, our specific heat of water, liquid water, I should put liquid. And then also our delta H fusion and delta H vaporization of water. Oh, and our specific heat of steam, my bad. Okay, so these again are all constants that we have to look up. Now, another thing, notice how the specific heat of the substance changes when it changes its state. So solid water, liquid water, and gas water, they all have different specific heat. So the specific heat for ice is 0.5 calories per gram degrees Celsius. The specific heat for water we know is 1 calorie per gram degrees Celsius. The specific heat for steam is 0.48. calories per gram degrees Celsius. And then the heat of fusion for water is 80 calories per gram. And then the heat of vaporization is 540 calories per gram. So there's all our given quantities, what we need in order to solve this problem. Now, another thing I want you to notice is we have this all in calories per gram degrees Celsius. So we are going to get our heat term in calories, okay? So in this example here, we're starting at ice at negative 12 degrees Celsius. So that's going to be down here. Remember, water melts, or solid water melts into liquid water at 0 degrees Celsius. So that's going to be this point right here is our 0 degrees Celsius. So we're starting below here. We're then heating to steam at 126 degrees Celsius. So that's above that boiling point of 100 degrees Celsius. So basically what's happening here is we're undergoing 5 different sections here. We have the first section where we're heating this ice up to 0 degrees Celsius, where it's then going to melt. So that's our second section. It's then going to heat up in the liquid state. So we're adding heat, the temperature's increasing in the liquid state. That's our third stage. It then undergoes another phase transition to steam at a constant temperature. And then we're going to increase the temperature from that 100 degrees Celsius to 126 degrees Celsius. So because of that, I actually need 5 different equations. All right. I know it's kind of a lot. So we'll call the first equation, we're going to call that number 1 to go with that number 1 on that heating curve. And here we're going from ice at negative 12 degrees Celsius to the phase change. So ice to liquid, I'll just say phase change. Phase change at 0 degrees Celsius, okay? So remember that delta means change, so that's why I wrote delta. So what we need here is we need Q is equal to MC delta T. The reason we can use this equation for this part of the problem is because we are changing our temperature, okay? So we have the heat is equal to mass, which they give us was 30 grams of water or ice. Solid water, right? C, we know of ice was, our specific heat of ice is 0.5 calories per gram degrees Celsius. And then the change in temperature is final temperature minus initial temperature. So that'll be 0 minus a negative 12 degrees Celsius because, again, we are increasing to 0. So that should be a positive change in temperature. And a negative of a negative is a positive. So we get 30 times 0.5 times positive 12, and we get 180 calories. So Q1 equals 180 calories. So that's our first heat or energy that's added. So number 2, we now have the phase change from solid to liquid. All right, so that is this part right here, this number 2. That's what I'm talking about. So phase change from solid to liquid, I know that I cannot use Q equals MC delta T because there is no change in temperature when we change phase. So because of that, I have to use Q is equal to M delta H. Now, because we're changing from a solid to a liquid, that is our heat of fusion. All right, so delta H fusion. So we get mass was 30 grams. Delta H of fusion, which we looked up for water, is 80 calories per gram. So our Q for that part of the heating curve, we get 30 times 80, and we get 2,400 calories. All right, so this is our Q2. All right, so that's the second part. Third part, we are now going from our phase change to our next phase change. So now we're in the liquid state, all right? So we have liquid, we now have liquid at 0 degrees Celsius to liquid at 100 degrees Celsius, because at 100 degrees Celsius, that's when we start to do that next phase change of turning the liquid into the gas. So that's going to be our parameters here, 0 degrees Celsius to 100 degrees Celsius. So again, the reason we can use Q equals MC delta T here is because we are changing temperature. So Q is equal to MC delta T for part 3. So our heat needed for this part right here, mass again is 30 grams. Our specific heat for liquid water was that 1 calorie per gram degrees Celsius. And then change in temperature here, final temperature is 100 degrees Celsius minus initial temperature is 0 degrees Celsius. So our heat added for part 3 will be 30 times 1 times 100. And we get 3,000 calories for Q3. All right, moving right along to number 4. So number 4 now will be our phase change from liquid to gas. So phase change from liquid to gas, we know that because we're going from liquid to gas, we're going to use the delta H of vaporization. And again, because we're at a constant temperature, we can't use MC delta T, so we have to use Q is equal to M delta H, and that's delta H of vaporization. So here, Q for 4 will be mass, which was 30 grams, times the heat of vaporization for water, which was 540 calories per gram. So we end up getting Q4 equals 30 times 540, which is 16,000 16,200 calories. And then last but not least, we now are at a gas phase and we're going from 100 degrees Celsius to 126 degrees Celsius. So again, because we have a change in temperature, we use Q equals MC delta T, and this is Q5. Now for this heat added, our mass again is 30 grams. This is the specific heat of gas, which was the steam, is 0.48 calories per gram degrees Celsius. And then our change in temperature is 126 degrees Celsius minus 100 degrees Celsius. So it's going to be 26 degrees Celsius. So we get 30 times 0.48 times 26, which is 374.4 calories. Now, we're not done yet. We wanted to know the total amount of heat that's needed for this whole process that we calculated. So what we do here, our Q total will be equal to the heat added from part 1 plus the heat added from part 2 plus the heat added from part 3 plus the heat added from part 4. I'm getting ahead of myself. Plus the heat added from part 5. So our total is going to be Q1, which was 180 calories, plus Q2, which was 2,400 calories, plus Q3, which was 3,000 calories, plus Q4, which was 16,200 calories, and last but not least, plus Q5, which was 374.4 calories. So adding these things all together, we get 22,154.4 calories total. So this is basically going through every single phase and phase transition you would need to in a calculation like this. However, sometimes in these problems, you might just be going from ice to liquid at 50 degrees or 90 degrees or something like that. Or you might be going just from liquid to gas or something like that, okay? So you don't have to use all 5 of these different steps. So ice, phase change from ice to liquid, liquid, phase change from liquid to gas, and then gas. You don't have to use every single one of those steps for every single problem like this. You have to really pay close attention where you're starting temperature wise and in what phase, and where you're ending temperature wise and in what phase. So just pay close attention to that. We'll do some more problems together in class, and I will see you then.